So,
Okay, yeah, so
to welcome back Theodore Drivas on simplicity, and he will give part 2 of his mini course on mathematical aspects of turbulence.
okay, thank you very much for again the invitation. So I just want to remind that last time we left off with this remarkable experimental realization that the energy dissipation rate of the flow, when properly normalized by the large scale lengths and velocities, tends to a non-zero constant, it seems, as Reynolds number, like the inverse of the viscosity, tends to infinity. Okay, so we can start today's lecture by Kolmogorov's 1941 theory, which uses this as a foundational tenet. Okay, so I'm going to just list the assumptions of the theory in a relatively simple way. We'll examine various parts of them in detail. So the first one is the one I just said, that this energy dissipation rate is bounded away from zero. In fact, really has a limit, is what he uses. And this is called the zeroth law. Then he made an assumption about the structure of the velocity field in the form of these velocity increments. So here I'm thinking about L as just a scaling multiple and Z hat as just some unit vector. And then this notation, delta L Z hat U, is U at X plus LZ, should be a hat, minus U at X. Okay, so there's just the increment of the velocity in the direction of Z with magnitude L. And his assumption about these objects were that they were homogeneous and isotropic in the sense that they have the same law for any point in the domain and for any direction vector Z and for L that lives in a certain range of scales. Okay, so this range of scales excludes things that essentially are at the same size of the container of the fluid, because at that scale, the motion is highly influenced by the boundaries of the domain, or just the container. And it also excludes things that are too close to the scale at which dissipation acts strongly. And this scale is denoted L sub nu. It's called the Kolmogorov length scale, and it's related to the size of the viscosity relative to the other features of the flow. The final assumption that Kolmogorov made was the existence of a unique exponent, h, such that this object, the increment, has the same law as this object when you have an arbitrary lambda scaling factor. So essentially, it's saying that the increments behave like the separation to power h, statistically. And this h for Kolmogorov is 1/3, which is the one consistent with this zeroth law, as we'll see in a bit. So taking these as just fundamental assumption, yeah.
Wait, how do you say the same? The statistical laws are the same? What do you mean? Just one of the moments? I don't understand.
Actually, so this is for any moment of this object has the same law as this object.
Oh.
Yeah. I'll actually say precisely just below.
Okay, thank you.
Okay. So these, so far, I mean, what it's based upon is this experimental observation. And then these two things that so far we haven't really given any indication that they're true. But apparently when Kolmogorov formulated this theory, he spent a lot of time looking at real data of turbulent flows, and he saw some inkling that this type of assumption might be borne out by those experiments. And so he just took it and ran with it and see what predictions he got. So a couple of immediate predictions from these assumptions are, number one, a quantification of this length scale at which viscosity is the dominant force, the viscous friction. And that scale is essentially obtained by balancing the flux of energy through a given scale with the amount that's dissipated by the heat term. if you think about it physically. Actually, another way to derive it is by dimensional analysis. It's the only length scale that can be written as this combination of viscosity and the energy dissipation, which Kolmogorov viewed as the only dimensional parameters you have floating around in the theory. Okay.
Did you say the physics thing again?
Yeah, the physics thing is that, okay, so when Kolmogorov makes this type of statement about how velocity increments behave as you essentially move the distance, you can use that information to estimate how much energy the fluid is passing through a given length scale. And in a couple of slides, I'll show you what I mean by that. If you estimate the amount of energy passing through an arbitrary length scale L, and you compare that to the amount of energy at that length scale being dissipated by the viscous heating, the friction, then when those two things balance is precisely this length scale L nu.
Okay, I see. So the idea is the friction is creating collisions and randomness and making more fluctuation, and so that heat energy is becoming fluctuation.
Yeah, it's a scale at which those effects balance. Yeah. So another prediction, and this is related to Dennis's first question about in what sense are the laws the same, is that if you look at the moments of these velocity increments at a distance L in the direction of L, this is what Kolmogorov considered. We'll consider something else shortly as well. And you take the pth moment of that quantity, this is, and then you average, long time average. Here I'm also averaging over separations and base points, but if you're in an isotropic homogeneous flow, this is unnecessary. This quantity I'm going to denote from now on by SP, because it's called a structure function, a pth order structure function, and I'll use these parallel lines to indicate that it's the structure function parallel to the separation vector, so you dot here that component. His assumptions say that this object should scale or should behave as a function of L, like epsilon L to the p over to the p over 3 power. Okay. There's one particular case of this which is privileged. It's the p equals 3 case, and this is the celebrated Kolmogorov fourfifths law. So when p equals 3, Kolmogorov had a derivation of this from the equations. This relationship between the energy dissipation rate and this third order longitudinal structure function is essentially a manifestation of this cascade that I've been referring to. Namely, it's a balance between the flux of energy through a scale, which is quantified by this cubic quantity in the velocity increment, as we saw, in fact, last time, and we'll see again today. So that balances the amount dissipated by the heating. And this relationship, again, is thought of as exact. Of course, what Kolmogorov did initially wasn't a rigorous proof of it, but later I'm going to describe a framework in which you can really think of this as a rigorous conclusion. And this, by the way, should hold only in the limit as Reynolds number really goes to infinity, and it should hold for scales that are, again, much bigger than the viscous scale and much smaller than the box scale. But this one is actually going to 0 as Reynolds number goes to infinity. So it should hold as L goes to 0 too. Okay, so his theory predicts this, but this one is also backed up by the equations. So it's a special case of that. And moreover, there's some more information. It's called fourfifths because the prefactor is fourfifths, and it's negative, which means that this quantity, which is not sign definite, it's just the pth power of some fluctuating number, has a given sign on average. It's this sort of skewness on average according to this balance. Okay. So now let's show how great this theory is in many ways. So the first thing I want to show you is just what do these things look like, and how does it compare to what Kolmogorov was saying? Well, here is some data from different Reynolds numbers. As I increase the Reynolds number, the color goes from green to red.
You don't have the same notation.
So this notation here is the same. So
you're
S2.
Doing S2. You're doing S2.
S2.
Okay.
Yeah, it's just the second moment instead of the pth. And so what you see is that for small scales, so as this L gets small, this object goes like R squared or L squared. So there is a notational difference between R and L. It should be L. And that's just a statement that at a given fixed Reynolds number, as you make L small enough, the field is smooth. So if you compute the square of the velocity increment, it should go like L squared. But then there's this range of scales that Kolmogorov identified as the inertial range. So that would roughly go from here to here at that Reynolds number. And it would go from here. It elongates as you increase the Reynolds number. And in that inertial range of scales, instead of going like the power 2, this object goes like a fractional power. And that fractional power is very close to 2/3. Okay, so this is what Kolmogorov imagined in the ideal turbulent regime. As you send this Reynolds number to infinity, this object would just look like that, just elongate to down to 0 length scale.
How it can be measured? So what is measured? So
yeah, so this is an example where what you would measure is an increment, and you would do that either by physically having some sort of hot wire that measures velocity at 2 fixed different points, and then you compute moments of it and average in time. So that would be one way to do it in a laboratory setting. Another way to do it is you have a single point and you just have a time series through that point, and then you take 2 different times and appeal to some sort of relationship between time and space increments. That's again a laboratory way of doing it. That uses something called Taylor's hypothesis. But what this is doing is numerics. And in numerics, you can just measure it. So as good as your numerical simulation is, you check convergence of the simulation, then you simply compute it. And that's what this is doing.
So it is simulation with Navier-Stokes?
This is simulation with Navier-Stokes, that's right. So this was done by Kartik Iyer and Srinivasan and some company very recently, quite high resolution, large Reynolds number simulation.
And real lab experiments also confirm? So
yes.
Consistent. Okay.
Yes.
And I notice it's bigger than 2/3.
Yes, that's a very good point. We can talk more about that. You're already sort of seeing ahead what's coming. So, but let's for now think of it as 2/3. So actually, okay, that comes to the next graph. Here's this relative difference from K41. So here what they're plotting is they take this exponent, they subtract the prediction that Kolmogorov made of P/3, and they just look at the relative error, so they divide by that, and they plot it versus P. And what you'll see is that at 3, where Kolmogorov made that exact prediction with the fourfifths law, it's the relative error is 0. It's just spot on. And then as Dennis points out, actually, as you go lower, suddenly the fluid is a little bit more regular. The exponent's a little bit bigger than 2/3. And if you go in this direction, suddenly the fluid is a little bit less regular. So the exponent is lower than P/3. And we're going to talk at length in a couple of slides about this picture and how to make sense of it and objections to Kolmogorov's original theory. But for now, let's look at it and say, well, these numbers are pretty small. Kolmogorov did a pretty good job with with his first theory, at least for P that are sufficiently small. Okay.
I mean, he was probably staring at information from artillery fire. They were I think they were trying to do statistics of how many shells you had to shoot at a tank in order to put it out.
Yeah.
Is there a way to understand those graphs as order dimension of an object, like a geometry?
Yeah, so you all know so much already. I mean, this will come in a bit. I'll talk about this at greater length. So now what about this exact prediction, the four-fifths law? Well, here is that third order structure function, longitudinal, and here's the linear increment. And you see that as Reynolds number increases, so these are two different Reynolds number, this one is bigger, the line where this reaches a value of 4/5, this range extends. And theoretically, if you were to go to infinite Reynolds number and extrapolate from this data, you would think, oh, maybe it just extends. And again, Kolmogorov's prediction is quite well borne out by the data in this inertial range of scales.
Okay, so what exactly is the 4/5? That's the answer to what question?
So that gives a relationship between the cube of the velocity increment in a certain sense with the dissipation and the length scale of that increment precisely. And that relation is given by the equation. Kolmogorov derived it, and the prediction is that the ratio of those two things was 4/5.
Okay, thank you.
Yeah. And here's another from the same data as the one we just saw above, the numerical data. You just see the same Reynolds numbers, and increasing Reynolds number means that you get closer and closer to the prediction of Kolmogorov. Okay. So now to this point that has already been sort of discussed, when you look at the theory, let me just actually first say that there's a relationship between what is typically talked about in turbulence, which are energy spectra, and the structure functions that I'm defining. Spectra are they're related to the Fourier transform of the structure function. And so if you have a 2/3 scaling for the second order structure function, the Fourier transform by the Wiener-Kitchlin theorem has a -5/3 scaling. So this prediction is the famous -5/3 scaling of Kolmogorov. And if you look, again, there are some deviations, but it's quite close. This relationship here, some other data from, I think, experiment. It's quite close to the prediction of 2/3. As we said just before, the third order prediction is supposed to be exact, right? So this is, again, falling into the p/3. So this would be p=3, and so it's 1. And the general thing says that for general p, you have some scaling, and Kolmogorov would say the scaling is p/3. Now, Landauâ said that the argument that this scaling should be like p/3 neglects essentially two things. The first thing it neglects is the significance of another dimensional number in the whole system. That dimensional number is the length scale of the box. I mean, the large scale, this capital L, what I called it. And the other thing it neglects is the fact that this epsilon is not really a constant. It's something that's fluctuating rapidly in space and time. And because of these two things, Landauâ predicted, that you shouldn't get this so-called monofractal theory where you have p/3 for this exponent, but rather this should be some nonlinear function of p. Okay, it should not be a constant multiple of p. Okay. So this is a plot of the energy dissipation. You can see that Landauâ is right. It's very intermittent. Certain regions have extremely high dissipation values, others have extremely low. This is actually from experiment, both in laboratory and the real world, like atmospheric boundary layer. And if you compute these exponents, just like Landauâ said, they are not linear functions of p. Instead, they seem to be some nonlinear function of p, concave function of p. The Kolmogorov 1941 theory is this straight line that says it's p/3. And the other things I've drawn here are I mean, I didn't draw, this is in Frisch's book and the data is from elsewhere, are various models. So these are the lines. The points are data of some sort. And let me pause.
Is there an abstract argument that it's concave?
Yeah, yeah. There's an abstract. It's just because it's just the convexity of the pth power. So you can argue that it's concave without I mean, exactly, but you don't know. Yeah.
There are a lot of concave functions. Yeah.
Yeah. And let me just pause 1 second to say that there was a period in time, and I think for many people this is still regarded as one of the most important theoretical problems of turbulence, namely to predict the values of these exponents as a function of p. And this is a problem that's called sometimes problem of anomalous dimension or anomalous of the scaling exponents. And there were many attempts to understand this using renormalization group, either in hydrodynamics or from models of it. And I'm just not familiar enough to be able to really comment on this, but I wanted to say it in case people want to look somewhere. And there's one model that at least I know of where great.
Do you have
Yeah.
any references there for this kind of?
I can provide references, certainly. One model where I know that this program has seen some great success is in the so-called Kraichman model, which is where you replace. So the dynamical system you're studying is that of a scalar field, which is just being pushed around by a velocity field, and it doesn't back react. So it's a linear problem. But that velocity field is built to look turbulent in the sense that it's a Gaussian. So it's built to look turbulent, but it has many simplifications. So it's a Gaussian random field that's white noise correlated in time, a so-called Brownian flow. And the covariance structure of that Gaussian random field is built to have an inertial range type behavior, just like Kolmogorov's prediction of the fluid. And in that model, you can study precisely these the dependence on p of these exponents. And in two limiting regimes, you can get like formulaic predictions. Those two limiting regimes are where you change the Holder exponent or the slope in the inertial range of the structure function. You make it very small, or you make the dimension of space very large. And it turns out that in these two regimes, you can get perturbative formulas for these things at finite p. And there are many names here that are relevant. I just list a few: Falkovich. Well, okay, they're here, and my notes will be online. So, and I can provide references also. But let me not say more about that right now. Let me say that this scenario is an instance of, I think at the beginning I mentioned the sort of division of labor work between mathematics and physics and engineering. This is an example where there's a lot of data and there are some theories, one even by Kolmogorov himself. This log normal theory was in 1962, his second paper in this direction. And then many others, which are somehow based on some phenomenological considerations, the beta model being a good example of one by Frisch and others. And then some based on just curve fitting, data fitting. And these things make predictions. I mean, you can fit them over a range of p and then test for larger p when you can do bigger simulations to properly resolve it. And so this is a good example of where mathematics can come in and try to, from this class of predictions, try to pick which of those are consistent with the equation and which may not be. And so as a general objective, we need to formulate a precise mathematical framework with which we can discuss these issues and really try to either make predictions or rule things out. And this is a big open area. I mean, I'm not going to have much conclusive to say about it, but these are some of, yeah, question?
No, it's just that Kolmogorov's was quadratic in p and the others were linear.
This one. Yeah. Maybe I won't talk about the details of the model.
Okay.
Yeah. Was there another question or? Oh, okay. So now I'm going to describe at least how I think about Onsager's contribution to this circle of ideas. And Onsager came around just a little bit after Kolmogorov. He may have even not been aware of Kolmogorov's work. I'm not 100% sure. But he looked at the same type of data and the same thinking. And he asked essentially this question, which is the one that we've been asking in a way. How is it possible that as you send viscosity to zero, the only mechanism in the fluid to remove energy, you can have a non-vanishing dissipation of energy? So the puzzle is that as you remove viscosity, you go to this beautiful Euler equation without this heating term. But this Euler equation, back at the very beginning, we saw conserves energy when there's no force, and otherwise it just has the balance with the force. And therefore, Euler itself doesn't seem to be compatible with this energy dissipation having a non-zero value. And so what Onsager said is here from his paper in 1949. He said it's of some interest to note that turbulent dissipation could take place just as readily without the final assistance of viscosity. And he said, in such an ideal turbulence, meaning sort of this infinite Reynolds number, infinite or zero viscosity limit of the turbulent flow, you couldn't obey any Lipschitz condition, and this is actually a Hölder continuity statement, with a Hölder exponent greater than a third. So you can't do it. Moreover, the ordinary formulations of the laws of motion, namely the PDE I just wrote down for Euler, have to be interpreted in a generalized sense. They're inadequate because the fields that you're obtaining in this limit are non-smooth, and making sense of that equation as a classical solution of a PDE becomes impossible. Okay. So yeah.
Where is that reference? Statistical hydrodynamics 49, is that where that is?
That's it. Yeah.
Okay.
So Onsager, his view of the generalized description actually originally was in terms of truncated Fourier series, but you can think about these things actually as weak solutions. So what we modern day call weak solutions, introduced by Leray, in fact. And the idea is actually quite natural from the point of view of the physics. It's to replace the PDEs with integrated versions of them. So you just regard them as balances of mass and momentum, and you ask that over any region, namely over integrated against any compactly supported test function, those balances be satisfied. And here the point is that even if the velocity field is irregular, all you need to have to make sense of this balance is square integrable. So once you integrate by parts, you put the derivative here. This balance makes sense as long as u is in L2. And so using this description, you can begin to talk about non-smooth objects. Okay, and this is a point of view that we're going to work with a little bit. So maybe, I'm sure many of you have heard the words Onsager's conjecture. Actually, in a way, Onsager just made a statement. He didn't really make a conjecture, but here's a modern day interpretation of Onsager's conjecture in weak, strong, and strongest form. So the weak form just says that if you're a weak solution of the Euler equation and you're in a class that's just a little bit bigger than C1, a little bit smoother than C1/3, then you conserve energy. So this is related to when he said it cannot satisfy a condition of that type. A strong form of the conjecture says that there exists an Euler solution with just less regularity, such that energy is dissipated. And finally, the strongest form of conjecture, and this is the physical one in a way, says that Euler solutions that dissipate energy should arise as vanishing viscosity limits of Navier-Stokes solutions. And the ultimate goal is to prove that the energy dissipation rate is bounded away from zero strictly by some constant for all viscosity. So that would connect Onsager's ideas back with Kolmogorov's ideas as a foundation of turbulence. So just one remark about these weak solutions. I mean, why weak solutions? There's no a priori justification of this in the sense that you can't prove from the equations directly that on subsequences, as viscosity goes to 0, you get weak solutions from Navier-Stokes. But what you can prove is that if you just had a little bit of compactness, then you could do it. Okay, that's clear. But that little bit of compactness is actually completely consistent with everything we see from the data. Namely, if you have that structure function defined like I did before, and that structure function satisfies just a bound with an arbitrary power of s bigger than 0, for a range of scales that's not infinite, but something that's ever increasing, that inertial range is quantified here. If that's satisfied, then any weak limit is a weak solution of Euler. So what that says is that if this—
I mean, as the viscosity tends to 0.
As viscosity tends to 0. And so what that says is that if this picture persists, like it looks like it does from the data, then one has much more regularity, in fact, than one needs to produce the compactness result to get weak solutions of Euler. So, okay, nobody's proved from the Navier-Stokes equations that you have this type of regularity uniform in the data, but let's take it as a well-justified assumption from what we can see.
And how is it compatible with this anomalous dissipation of energy mentioned last time?
Right. So the anomalous dissipation of energy would say that— I'm actually going to comment on this a bit more later, but it would say that if this holds for S too big, if S is bigger than 2/3, then there— well, actually, no, it's not 2/3 here. It's a slightly higher number. I'll talk about that. Then there can be no anomalous dissipation of energy. So to be simultaneously consistent with anomalous dissipation of energy and that weak solutions describe, you just need S to be less than that given number, which is strictly less than 2, and positive. But everything that we see is consistent with this. There's no contradiction. It's exactly consistent.
So, but this anomalous dissipation of energy is actually observed. So you anticipate that the regularity will be less than.
Oh, actually, yeah. You anticipate the— I mean, in terms of what you anticipate this S to be much bigger than 0, consistent with the anomalous dissipation of energy and everything else we know. It's just you can't prove it. Yeah.
Well, so the weak conjecture is proven now, isn't it?
Yeah, I'm going to talk about that. Yeah.
Yeah, but but he wanted to know. So the answer was yes to his question, maybe.
Well, okay, can you repeat the question one more time?
Misha,
So—
what can I think the answer was yes to your question.
Yeah, I guess so. So that the solutions could not be too regular, I guess.
they can't be too regular, but that 2 is some number that's— think of it as 2/3. It's not exactly 2/3, but it's some number.
Wait a minute. Yeah. These are different numbers. And the easiest one to remember is the Holder exponent of 1/3 is critical, right?
Right, right.
So you're saying that it's known that it can't be more regular than 1/3.
Yeah.
I mean,
of course,
a mathematical thing that's consistent with experiments. Oh, wait, but no. Yeah, if the regularity is greater than 1/3, you can prove conservation of energy. There's no anomalous dissipation. So, but you observe anomalous dissipation. So in real life, the regularity can't be better than 1/3. So that's known. In real life, the regularity can't be better than 1/3.
Yes.
And what does this mean about S?
So this is just— So this is just saying if you have any modulus of the structure function, any uniform modulus in viscosity, then you have enough compactness such that vanishing viscosity limits are weak solutions of Euler. That's certainly not incompatible with the whole discussion of anomalous dissipation. It just says, as Dennis pointed out, that physically speaking, we know that you can't have this modulus if S is too big. Let's call it 1/3, just to say a number. But if S is too big, then it would contradict the anomalous dissipation. But in reality, S is seen to be smaller than that number. And mathematically, all you need is that it's positive. That's all I'm saying.
Theo, may I ask a question? So in principle, Hölder exponent can depend on a point and even on direction. And
Yeah.
so you can think that there is a spectrum of possible exponents, I mean, depending on point and direction. So how this multi-scaling or multifractality affect this conclusion? So how much of one do you need to have?
Right, yeah, so that's a great point, and I'll talk about that a bit later too. But let me first remark that this structure function is an averaged object. So,
yes, but if you think about Hölder exponent for the velocity field.
Right, right. So in a little bit, I'm going to relate those two ideas, namely the sort of size of the sets on which the velocity is Hölder of a given exponent, how that's related to these exponents zeta. I'll talk about that. But maybe just in a little bit.
No, but my question is basically the condition for having anomalous dissipation should we formulate it in terms of structure function, which is just a moments, which is kind of sums or integrals, or in terms of the Hölder exponents of the velocity field?
It should be in terms of structure functions, and I'll formulate it like that just momentarily. The reason why Hölder is discussed in this whole circle of ideas is actually historical. I mean, honestly, it shouldn't be, because the correct criteria, as is demonstrated by other equations like Berger's, is at the level of LP spaces. So they're about structure functions. The 1/3, and the reason why Hölder is discussed is simply because Onsager said it. I mean, he just said a Hölder criteria. That's the way he was thinking about it at the time. But as I'm going to explain on the next slide or something, it's really the structure functions that matter, as you say. Okay. So let's try to just understand this a little bit more in detail. What goes into whether or not you conserve energy. And I'm just going to do a baby calculation here in terms of the nonlinearity in the fluid. So the only question is about whether for a non-smooth velocity, the nonlinear term can change the energy, the level of the energy. And so let's analyze. So the nonlinear term, I don't know if I wrote it here, but this is what it is if you compute it in the energy. So I'll just write, so it's like, it's u dot grad u, and now I'm going to look at the energy. So I'm going to take the inner product with u. So this is the term I'm looking at, and here I've written it with v, but okay, that's the term. So in index notation, if you like, just to see where all the contractions are, it looks like this. Doing some manipulation using just chain rule, I can write this as the gradient of some scalar function, and this is the velocity dot that gradient. I integrate by parts, I put the derivative here, I get a divergence. The divergence is 0. So when I do this calculation, I assume everything is smooth enough to do all these manipulations. But what did we really use? That's the question. So what we used here naively is that the velocity is c1. But what we need really, you can think heuristically, is that in order to justify these integration by parts, we really just have to put a derivative here. We have to split this derivative over 3 different v's. So that's naively just 1/3 of a derivative on each u or v. And that sort of at a very heuristic level shows you why the 1/3 exponent comes up in terms of whether or not you conserve energy. Okay.
Well, what does the colon in the formula mean?
It means contract over both indices. So this is a matrix. It's the outer product of the velocity vectors. This is a matrix, and you just trace. You just contract these 2 matrices. Anyway, okay. It's just notation.
Okay.
Okay, so now let's try to give some more. Wait, Misha, did you have a question?
No, I just asking whether where your distribution comes from, so which you mentioned last time. This.
Yeah. Wait, the distribution.
There was some important distribution that you alluded to?
That was the distribution related to the development of finite time
yes.
singularities. Yeah.
Yeah. No, but in fact, you're exactly right. In the context of the Navier-Stokes equations, it's exactly that term, that is the distribution. You can give meaning to that term as a distribution, and that's right. That's right. And it's the same term for Euler. It's just that, yeah. Okay. And we'll see that again in a second. So now let's understand how to sort of think about this more precisely. And in order to understand how energy passes through scale for some rough object, you want some notion of decomposing the object in scale. And so you could do different things. One way to do is coarse grain. So you just mollify the velocity by convolving with some scaled mollifier G. Another way you could do is just project onto the low modes in Fourier if you have, say, on the torus. And the picture is this. You have something like this is my background, and you just smooth it. And now the remark is that the reason why you can study the energy with this type of operation is that if you're just square integrable, I mean, if you just have finite energy, and you define approximate energies by means of these mollifiers, so the energy contained in length scales bigger than L, because you've sort of cut out the scales less than L, well, those energies converge to the physical one as you send L to 0, just using this integrability. And same with the Fourier, if you do it like that. So, okay, now with this object, we can start to understand how it changes with non-smooth velocities. All we need is some integrability to make sense of it. So in order to study it, we take the equations of motion, which are interpreted in the sense of distributions. And technically speaking, you choose the test function in the right way so that the result is an equation for just the large scale velocity. So this is the mollified velocity. And I made it look just like the Euler equation. So this part is just like Euler for the large scale velocity. But then you incur an error term. And this error term is just a commutation error from trying to commute an averaging procedure, namely this mollification, with a nonlinearity. And so I just rewrote trivially what you get with what I wrote here.
So these are the famous cumulants of statistics. Exactly.
Yeah. These are cumulants, and this relates to something we discussed last time, which is this closure problem. So the closure problem for an engineer in particular is if you want to only model the large scales of the flow, which are captured by this U bar, and you want to do that on a computer only keeping track of what happens at those large scales, you need to postulate some functional dependence of this term here on the large scale field. So you need to write this as some function of this. And that step, okay, it involves derivatives and things like it's not just that, but that step is called the closure problem. And that's a whole field that I'm not going to talk about, but it may in fact be related to renormalization, because in a way, if you send L to 0 and you get sort of a limiting thing, like an effective theory in that limit, maybe it could inform how you do modeling at finite L. But let me not speculate too much. Okay, so now with this decomposition, I look at the rate of change of the energy in those large scales, and I see the only contribution is from this thing I call pi. And pi is the work done by the stresses here on the large scale gradient. Okay, so it's just this interaction between some variation of the large scale thing with the stress. And this is responsible for all the transfer of energy. So all the energy that's passing in and out of the large scales is through this thing called pi. So in light of that, it's sometimes called, the thing responsible for the turbulent cascade. And this is a picture, which is actually, I think, first proposed by Louis Frey Richardson, which is why his picture is here. But anyway, the picture is that energy is injected at some large scale. So it makes these large scale structures. Think of them as big vortices. And then the dynamics of the fluid kicks in. And then these big vortices split into smaller vortices. these smaller vortices again split, and here it's like a doubling, splitting, but okay, this is just a picture. And in this range of scales, which is quantified by this inertial range idea, there's a constant flux. There's a flux of energy by pi that takes energy from the large scale down to the small scale, at least in 3 dimensions. Eventually, you reach a scale at which the viscosity acts, and then the viscosity takes the energy out of the flow. The point is that if you have dissipation independent of the size of viscosity, then it must be the case that this cascade is efficient enough to transfer energy all the way from here down to here in a way that doesn't depend on the fact that the viscosity is getting smaller and smaller. And what I'm going to describe to you is a theorem about what regularity the fluid must not possess in order to be consistent with that type of efficiency. And I just wanted to include this nice poem because it captures some of these ideas. Big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. And that, I think, quite beautifully captures this cartoon. Okay, so on the last slide, yeah, was there a question?
Would it be possible to sort of represent this energy transport from big scales to small scales as certain transformation in certain functional space of, well, Fourier modes or something? So is some transformation just acting from one scale to the next scale, and so you just kind of compose these transformations
So,
by one?
Yeah, that's an interesting question. So let me say one point that would suggest that maybe you could think of it like that. So one point is that the cascade is known in certain quantifiable senses to be local in scale. So the flux in particular is local in scale. Namely, if you look at the contribution to this pi, and you decompose the U that it's acting on into bands, scale bands, then you can show that outside of a neighborhood in scale of this given L, the contributions of those bands are very small, which suggests in some sense like this stepwise progression of flux through scale. However, that sense is not, it's not clean like that. I mean, there are certainly, there could be highly non-local interactions in scale space that do make some sizable contribution. It's just that in some average sense, they're small. So to answer your question, I think there was certainly a hope that this type of thinking could be applied to turbulence, and maybe there's been some success, particularly in model problems where you discretize the flow in one way or another. But for, as far as I know, for hydrodynamic turbulence, it's not clear how one would really connect to that picture. And one possible fundamental issue against it is the non-locality of this object in terms of scale, both large and small. So, but maybe we could talk more about it. There are some models where perhaps you can really think of it that way. These models are called shell models. So.
Okay, thanks.
Yeah. Okay, so what we proved on the previous slide is that the energy is constant on this interval of time, if and only if the limit of this flux object goes to 0 as you send the scale to 0. Because we had this equality and we showed that the resolved energy goes to the real energy. Now, if your Euler solution arises as a 0 viscosity limit, which, as I said, is somewhat conjectural, but a very, very mild assumption proves it, then you have a balance between this flux and the dissipation by viscosity, this anomalous dissipation. So it's saying that as you send the scale to 0 and viscosity to 0, there's really a correspondence between the cascade that's pushing energy through scale from the nonlinearity and the viscous heating, which is becoming effective only now at infinitely small scales. And this correspondence was first rigorously noted by Duchamp and Robert in 2000, but it underlies Onsager's ideas. So I think he understood this maybe at a different level of mathematical precision. And let me remark that this balance is related directly to this Kolmogorov fourfifths law. That just this structure function, third order cubic thing, is somehow related to this, and then it balances the dissipation. And you can connect these things rigorously. So when I say the fourfifths law is exact, what I mean is there is some very mild assumption about compactness of the Navier-Stokes solutions that if it holds true, the fourfifths law is a consequence of the equations. And so it really should be regarded as an exact statement. And here's just a reminder of the success of the fourfifths law, okay, albeit limited, but at relatively small, numbers far from infinity. And this correspondence here has also been looked at in the data, and you can see again, quite a nice success. The ratio of these two things is close to 1 in a large range of scales. Okay, so again, by the way, it seems like it's almost time up, or is that true? No, do I have more? I have until 4, is that right?
Well, you have at least 10 more minutes and then
okay.
Discussion. Definitely.
Okay. So in light of what we just said on the last slide, we know that whenever you can show that this goes to 0, energy is conserved. And now the question is, how do we quantify how big this is? What regularity spaces should we think about in terms of the velocity in order to quantify its size? And it turns out that the right spaces, and I think Koch mentioned this, are those that are LP measurements of the regularity. And these go by the name of Besov spaces. They are directly related to structure functions. So let me tell you what they are. A velocity belongs to a Besov space with index sigma infinity p. And I'm always going to think about infinity here, so you can forget it. For p bigger than or equal to 1, if and only if it's in LP, so pth order moments are finite, and the increments in LP satisfy a bound like L to the power sigma. So said another way, these increments are just related to the structure function by the 1 over p power. So this bound is really a bound of the form p times sigma for the structure function, which we've seen before, and here's just another plot of it. I'm considering different p, and you see that the structure function shape changes, but in this range of scales, it always looks like a straight line, and these spaces are defined by the sort of a bound to this straight line of this is on the log-log plot, so a bound of some power.
So did the spaces appear in this context, actually? Were introduced in this context? Or?
No, they existed before this context, but they were first introduced in this context by this beautiful short paper by Peter Constantin, Wayne and Idris Titi. And this is, so let me state the theorem because it's directly relevant to your question. So this is a paper that appeared actually after a paper of Eyink, which did essentially a restricted version of this question, assuming something like Halder space, not exactly Halder space, but then the result of this one is sharper and also closer to what we see in the data. And the statement is this, that if you have an Euler solution, a weak Euler solution that is continuous in time with values in L2, so that's a statement about the energy, and L3 in time with values in this Besov space, which just means that when you look at the third order structure function and you average in time, that thing satisfies a bound of the form r to the power p or 3 times this number sigma. So it's just a statement about the integrals of structure functions being bounded by some particular power law, just like in this picture we see. And they said that if sigma is bigger than this number 1/3, then energy is conserved. So it gives a precise quantification for what type of irregularities must develop in the flow in order to be consistent with the flux of energy being strong enough to push stuff out at 0 length scale when viscosity goes to 0. Okay, so this is really the correct space, as we'll see actually shortly, for thinking about this problem. This or some slight
So in
refinement of
words,
it.
I still don't know what the space is. In words, how do you say it?
In words, you take the velocity increment at a given scale L, you measure that in L3, and so L3 of the base point. The increment depends on a point in space and also a neighboring point, this L. You average that, you cube it and average that over the domain, and then you integrate in time from 0 to capital T, where we're looking here. That object has to satisfy an upper bound of the form L to the power 3 sigma.
What's
So
sigma?
for the BS of
Sigma
space,
Well, what is
sigma
sigma?
is here. Sigma is going to be some number that's bigger than a third, but at the moment it's the thing defining the space that you asked about.
so
Yeah,
you
well,
can
they-
think of sigma as the Helder, the smoothness index.
Right,
3 and infinity are Lebesgue indices. BS of spaces, B sigma PQ, in here we have P equal to 3 and Q equal to infinity. They generalize. This is a nice interpolation a family of spaces that contains when P is infinity. So B sigma infinity infinity are precisely the sigma Hilder spaces. So
That's
these,
right.
these spaces give better tools than Helder spaces. And I mean, that's how I understand it. That's why Konstantin and Ian Titi use them because they naturally provide, as I said, better tools than Helder. So think of sigma as the smoothness index.
That's right. Yeah. Thank you very much. Yeah, it's exactly that. It's, if you want, it's the number of derivatives the velocity has in L3. Yeah. Okay. So I'm not gonna. Well, okay. Maybe I'll just outline the way this is proved is actually just very simple. So the main observation is that this cumulant, as Dennis said, this cumulant, given that it's a cumulant, has a very nice reformulation. It's defined in terms of the average of the product minus the product of the averages. But actually, because it's a cumulant, you can, and you think of it as like a random variable, even though, okay, it's deterministic here, but I think of R as being, this is a density, and I'm thinking of integration as a average. Cumulants are invariant under deterministic shifts. So you can actually sneak inside the velocity at a fixed point x if you're integrating over a point x plus r. And what appears in the definition of the cumulant is now not just the velocity, but the velocity increment. And this is the key idea behind this proof, because the same is true of this large scale gradient. You again have velocity increment. And now this flux of energy through scale is quite simply related to a cube of the velocity increment through these formulas. And you get a bound, as Gerard was saying, you just use now the definition of the space, and you have this quantification of how big this flux is as a function of the scale in terms of the regularity index of the solution. If the solution has more derivatives than 1/3 in L3, this goes to 0 as the scale goes to 0. So the cascade slows down. I mean, it's not efficient enough to work even at 0 length scale. And so the physical statement is that you need to develop motion or irregularities that are fine enough in order to have this persist, to break, to essentially move away from the context of this bound. So just a small remark to make it sort of more connected to the Navier-Stokes equations. You can get the following statement. If you have a sequence or a family of Navier-Stokes solutions, which have the property that the structure function satisfies a uniform bound for some exponent sigma. So this is again the same Besov space. So I'm saying uniform in viscosity, the solution has sigma derivatives in L3. Then you can quantify how big the dissipation is. You can say that it's bounded by a given power of the viscosity, and that power depends intimately on the the regularity that's uniform in the viscosity. So it shows that whenever sigma is bigger than 1/3, it goes to 0, and it goes to 0 with a certain rate. Okay, and of course, what one expects is that it doesn't go to 0, which means that sigma has to be less than or equal to 1/3. I want to say that in light of this statement, all the experiments that we have observed about the dissipation not going to 0, even if it were to go to 0 as you increase Reynolds number just very slowly, like a logarithm or a logarithm of a logarithm, they all point robustly to Euler solutions with singularity because of this theorem, in fact, because if you had a bound of a given power, if you had a lower bound of a given power, then it would imply that you couldn't remain uniformly in a space like this. So you have to develop singularity as viscosity goes to 0. So,
on the left side, what do you have? U to what power?
On this side?
On the left side, yeah.
Yeah, the left side is just saying that the solution is...
No, what is that symbol, the power?
Oh, nu, viscosity.
Thank you.
It's just, yeah, okay. Okay, so here's actually Dennis sort of envisioned this at the end of last talk. Here's some precise formulation of a mathematical goal that you might have in making and giving all of this foundation. So the first, and I think really most important thing here, is to show that for some data at least, and for some time, and for some value not 0, bigger than 0, there's a uniform bound on the Navier-Stokes dissipation due to the viscosity and potential singularities, which have never been proved to exist, but let's include it, that keeps it away from 0, uniform in the viscosity. So this is just precisely what do you mean by anomalous dissipation. The second point is to show that this family of solutions of Navier-Stokes is actually compact in certain spaces, in spaces that are strong enough to allow you to converge to weak solutions of Euler. So for example, just L2 is enough to converge to weak solution of Euler. The third statement is that those weak solutions that you converge to should exhibit this constant flux, namely this pi, as you send L to 0, should balance the dissipation, and the solutions should live in accord with the Kolmogorov fourfifths law in a space that's like Besov 1/3, so a space that has essentially 1/3 of a derivative in L3. And if you establish these 3 points, then you've given some really rigorous version of what we see in the experiments thus far, at least in certain situations. Now, everything here I've said is just for maybe some data, some time. Typically, you want to go further. I mean, you want to say that the behavior is generic, and maybe you're in some statistically stationary regime. And so there are many variants of this that you could ask. But here I'm just asking for this one. And there are model problems, a notable one being the Burger's equation that I'll talk about at some point, where this mathematical dream about a statistically stationary regime and genericity was actually borne out, and I'll make mention of that. Okay, so I can keep going a little bit, or?
Well, take another 7 minutes maybe.
Okay. Okay, so now I think somebody asked about this. So let's explore some consequences of this theoretical point of view. So the first point is that these integrated senses of regularity mean that point to point, the Holder exponent can change. So this was something that was mentioned earlier. It's just now in an integrated sense, you have some fractional number of derivatives. Point to point, the Holder exponent changing is actually the mechanism for this exponent to be a nonlinear function of P. And we'll see that in some examples, precisely why that is. But that's sort of the one mathematical way to think about this nonlinear dependence on P, is just that the fluid is spotty in its singularity structure. Somewhere it's smoother, somewhere it's not. Now, this is going to be a bit heuristic. So there's something called the multifractal formalism, which was a way to make precise this connection. And I alluded to it earlier. It's work of Parisi and Frisch. And they said the following. They said, assume that you have local Holder exponents that depend on the point that you're at in some given range between h min and h max. H min, something bigger than 0, h max, something less than 1. So they're saying that point to point, the fluid looks singular locally, and the local singularity is something that's strictly less than 1, but also strictly bigger than 0. That was their starting assumption. Then they said, okay, let's define the set S of H to be the set of points X such that the local Holder exponent was equal to H. Okay, so that's saying like the set of space where it's really Holder H regularity. And let's call D of H the dimension of this set. And the dimension here, I'm being very vague because there's no precise statement to be made yet, but you could think of it like the box counting dimension or the Hausdorff dimension of this set if it were really made precise. But for now, let me be vague. Now, by the definitions of these things, if you have X that's within a distance R of this singularity set corresponding to Holder regularity H, then the increment of velocity at that X for separation of that R should be like R to the power of H. Now, based on the dimension, you would expect that the fraction of such points, so X such that the distance to that set is like R, goes like R to the codimension. So this is D, the spatial dimension, minus the dimension of the set where your Holder H regular. So Parisi and Frisch used this to relate the exponents of the structure functions to the fractal dimension of the set where your Holder exponent H. What they said is that if you look at the structure function here, and you assume that there's some continuous density over Holder exponents, let's denote it by d mu, then I can write the average of the pth power of the increment as an average now over those Holder exponents H. And for each H, when I'm on that set, I just decompose space into those sets S of H. And when I'm on the set where I'm Holder exponent H, this increment is exactly L to the power H. So then to the P power, you get this contribution here. The fraction of space that you occupy is exactly L to the power kappa of H, the codimension. So that's this contribution here. And now I just integrate this according to that density, this hypothetical density, from the range of exponents that I have. And I declare that as I send L to 0, this should behave asymptotically like L to the power zeta p. Zeta p precisely is the limit of the ratio of the logarithms of these quantities. So you can define it as like the logarithmic derivative of the structure function. And now from this formula, together with the steepest descent or whatever, you get that zeta p is related to a variational problem. It's the infimum over H in that range of this quantity here, which is the exponent of L. So this is a precise theoretical prediction. It says that the amount of regularity the fluid has in a given LP, when you measure it in a given LP, is related to a geometric property of the structure of the singularities, namely the codimension of the set on which it's Holder exponent H, and there's some variational way to pick out which H corresponding to which P. The Legendre transform of this statement gives you a prediction about the dimension of the set on which the fluid is Holder exponent H in terms of these zeta P's. And in fact, this is a useful way to look at it, because you can't measure, or it's very difficult to measure, the fraction of the space on which you're really Holder exponent H, but you can measure these zeta P's. They're an average quantity, and you saw the ranges of scaling. They were pretty clear, so you could hope to measure these zeta P's. And now you just have to compute the infimum of this function, given these zeta P's from data, and suddenly, given an H, and suddenly you have an estimate, according to this theory, of the fractal dimension of the set on which the fluid is exponent h. And so here's a plot of this type of thing. So from some data, you see that for different h, this number changes, and there's like a most probable one, according to this plot. And this most probable one corresponds to some number just a little bit bigger than 1/3. So what it says is that according to all these things, the fluid is slightly more regular than would be required to dissipate energy most places. And in fact, the set on which energy dissipation happens, the set on which the fluid is sufficiently irregular to continue to dissipate without viscosity, is actually has measure 0. It's actually a set with dimensions slightly less than 3. So these are the types of considerations that come from this circle of ideas. And okay, maybe it's best to stop here, or maybe 2 more minutes. That's okay.
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 Got it.
So I already made this point to Misha's question. So there's a precise sense in which you can say this cascade is local in scale. And some references here are Eink 2005, and then Konstantin, Cheskarov, Friedlander, and Schwittkoy 2008. In this latter paper, they used Littlewood Paley to precisely decompose the flow into bands of scales, and they show that away from the given scale h, you can quantify how much the fluid at larger or less scales affects this quantity. And here's just another application of Onsager's ideas. It says that now it's a statement relating the irreversibility in terms of the Eulerian land of energy dissipation to a Lagrangian form of irreversibility. That is, irreversibility at the level of particle motion. And so the theorem says this: if you have an Euler solution, a weak solution of Euler, which is an L3 space-time, then the flux, this anomaly, this pi, which is the flux of energy through 0 length scale, equals, in the sense of distributions, the following quantity defined by a number of limits. What this quantity is it compares the dispersion or separation of particles that start at a distance r and go forward an increment of time tau and move in a smooth version of that velocity field u. So it takes their separation forward in time and backward in time. So actually this one's backward in time because you have a minus tau. This one's forward in time, you have a plus tau. So you take those differences and rescale or renormalize by tau cubed. And then you send all of these parameters to 0. So you're really looking in a small region for small times, and you're just extracting this cubic behavior in time of particle splitting. So a picture is like this. Time is going forward. Okay, I'll explain this picture in 1 second. And these particles are moving with a mollified velocity field. Now, as we said before, Duchamp and Robert proved that in 3 dimensions, under pretty mild assumption, this pi matches the energy dissipation, the anomalous dissipation, which is positive. In 2 dimensions, the situation is very different, but you can do a setup in which you force with a very small scale forcing, and you take that forcing wave number to infinity. And then what you would get is that this flux matches an input by the force, which is anomalous, just like the energy dissipation is anomalous in 3D. Now in 2D, this work done by the force would be anomalous. And it comes with a minus sign, and typically this is expected to be, this I is expected to be a positive quantity. So the force adds energy to the flow. And so then this whole thing would be negative. So the point is that the flux in 3D is a positive thing. Energy is going through 0 scale from top to bottom. It's losing energy at 0 scale. And in 2D, energy is coming from 0 scale into the fluid. So it's gaining energy from nothing, if you will. And this difference in sign is a signature of irreversibility. And this theorem shows that, in fact, it's related to whether or not particles move away faster from each other if you go forward in time or backward in time. And so in 3D, particles tend to split faster backward in time than forward in time. and in 2D, the reverse. They go faster forward than backward. So in principle, if you had a movie of a turbulent fluid, you could think about figuring out which direction time is moving. Say it's being stirred, so you can't see if it settles or something. It's being stirred. You can think about which direction time is moving by looking at all the little particles in the flow and trying to play the movie first forward in time and backward in time and track how fast they spread away. Take the difference and do this procedure, and you'll figure out which direction time is going if you're in 3D or 2D. And just final remark, this analysis actually is based on a relation known in the physics literature called the Ottman-Goetzky relation, sort of just makes that rigorous and precise in this context. And this observation, at least in 3 dimensions, that there's some irreversibility that can be seen like this is from a paper of Juka et al. Again, a physics paper, and this is just a precise statement. So, okay, maybe I end there for now and we continue next week.
Thank you.
Questions and comments?
So you mentioned these discrete models. So how well are they developed compared with continuum models? So
yeah, that's a good question. So it's an interesting story. These discrete models, I think, were pioneered by people like Kazan, and the hope was that, first of all, there are analogs of everything I said essentially for these discrete shell models. You can think of them as just representing the dynamics in Fourier space at like a geometric progression of wave numbers. But they replace the velocity vector field with just a scalar function now, and it could be real or complex. And they truncate the interactions in the nonlinearity to include just certain terms. They prune. So if you Fourier transform Navier-Stokes equation, in principle, you have interaction between all the wave numbers. You have some, it's a convolution in wave number space, the product in physical space. And the shell model just prunes those interactions and keeps triadic ones at the level of the, so it just keeps certain interaction so that the resulting model has certain similarity with the original one, namely that there's some energy that's conserved or some other quantity depending on what it's trying to actually capture. So there are a whole class of these models. They go by the names of things like Sabra, Goy, dyadic, various models of this sort. And each model actually, the properties of the model vary in terms of how well they're understood, depending on which one you look at. One of them, the dyadic model, is essentially as well understood as the Burger's equation, which is another example of a simplified setting in which you can say a lot more. So in my head, I equate those two in terms of our knowledge of them. I'm not going to talk too much about that now. I think for some reasons, that's not, it misses a lot of the interesting turbulent behavior. In fact, you don't have intermittency in that model. You have like a K41 type spectrum, but that's perfectly understood in a way. The more interesting models are the Sabra and the Goy, and there are even others. And those models display this, if you compute the structure function now with the shells, they display the same type of anomalous scaling. Mm-hmm. And they were, and moreover, the scaling is remarkably similar to real Navier-Stokes turbulence. So there was a big effort to understand the scaling in these models by people like Kadanoff and others. And my understanding was that at the end of all of those efforts, it was essentially determined that the shell models were just as difficult to understand as the real flows in many ways. I mean, not much more is known there than is known for real turbulence. And so there needs to be some new idea in that direction to really progress. And yeah.
But in the shell models, there is a renormalization operator, isn't there?
I suppose there would be. I mean, they're discrete models, so you could probably really put it into that framework.
Well, it was a lecture course on hierarchical models just before your lecture course. And in
Oh,
some
yeah.
ways, hierarchical models are similar to shell models. Their relation to normal statistical mechanics, more or less like relation of shell models to turbulence.
Oh, I see.
And Hani, do they have renormalization, the hierarchical models?
Yeah, that was a talk of Blecher about.
Yes. Okay. So, I mean, in answer to Misha's earlier question, since you've just said they, in the final analysis, they're just as non-trivial as the full problem, they do have renormalization. So that would be a nice place to warm up with renormalization ideas.
Yeah, I think that would be a really good area where there could be some cross-fertilization. Fertilization. Yeah.
I just had a naive question. So to what extent the fact that the non-dissipative version of Navier-Stokes is Hamiltonian is useful? So put in other words, if you take a Hamiltonian PDE and then you put for some reason some dissipation, would you have the same kind of results?
So I guess there's maybe, okay, I'm not sure if I will answer this, but there's an issue of in what sense are the dynamics Hamiltonian? So for Euler, if you're smooth solutions, I think you can make sense of that and derive a lot of consequences of that. But here, the relevant Euler solutions seem to be those, or at least I've been arguing, that they're those that possess less regularity than is required to even make sense of the equation as a dynamical system in some space. And so there are just these weak solutions, and the structure that they have or what they share in common, I mean, it's a big question. I don't know. But I would say that if you ever have this very singular behavior, it's indicative of the limiting model being in a regime that's really not very nice, and it may be difficult to make sense of the type of properties that you would typically think about.
But wait a minute, you passed over the sort of abstract formulaic question of, is there a Hamiltonian formulation of Euler just as an equation without us worrying about any analysis? It's an algebraic question. And then he said, I think his question was like, as if you were assuming that's true, and then you add, do you have such a formulation in mind, Hanin? Hamiltonian formulation of Euler?
Isn't it done in the book by Arnold and Chazin?
Do you always
Yes.
answer a question with a question?
Yeah, I guess, yeah. Because it's basically like a rigid body, huh? Infinite dimensional rigid body.
Oh, I see. Yeah. Okay. Yeah. The infinite dimensional. Well, yeah, but that's not useful.
No, that's the point. In fact, because in all the computations, basically, you never use this. Maybe just L2 conservation of dissipation, but nothing more, basically, no?
So
well, I think it's a good idea to use the Hamiltonian formalism, but where is it really in a useful way?
So tell us, so in this Kolmogorov's story, are we supposed to think of the velocity field as some random field, I guess? True, there is some average, and so we forget about Navier-Stokes. It is just some random field with certain properties of scaling properties and certain homogeneity, etc. Does this have a good mathematical foundation, this kind of random field approach?
Okay, yeah. So what I'll say is this: you can build random fields. Okay, first to answer your question, yes and no. For the yes part, in terms of thinking about like a monofractal field, namely there's just one scaling exponent, homogeneous and isotropic, such objects can be built as random fields. And Kolmogorov, indeed, I think that part of his theory, he wasn't thinking about the connection between that. I mean, not that he wasn't thinking about it, but he didn't make really a precise statement about the connection between that and the Navier-Stokes equations. He just took that as a basic assumption of his model, and so that can be made precise in terms of theory of random functions. You can construct them, but then there were aspects of Kolmogorov's theory which were really model dependent. The principal one is the fourfifths law that actually follows from the equations of motion, and so that was an exact constraint that guided his theory and his thinking, I think. Now, the statement of the fourfifths law says something quite precise about this random field. Namely, it says that the flux that you can construct from the Navier-Stokes equation, some cubic in the velocity object, the flux matches the dissipation. And the dissipation is something that isn't contained in a theory developed just for random fields. And so you could in principle construct that flux, but to know about the dissipation, you have to go to the dynamics. Maybe let me also say this. The regime of validity of any of these theories is very much, or these predictions is very much up for debate. So there's a question: do you really have to go to long time and think about long time averages before you do any of this? Should you be adding some noise in the problem data or force or something before you do any of this? And there are varying degrees to which people can check those things. And I haven't really talked about them so much here. I'm really thinking more of being in this turbulent regime where we see this phenomena, these structure functions and all these things deriving consequences when you're there. But the question is, when are you there? When do you get into that situation? And Kolmogorov, I think, at least from what I read in books like Arnold Kazan, his original thinking was just trying to make prediction about the turbulent fluid with whatever he could do with the equation, but also adding external input which wasn't mathematically reduced from the model. And he later posed a precise mathematical setup with which you could hope to build up the theory from scratch. And so that was supposed to be my lectures 3 and 4. It may turn out to be 3.5 and 4, because I still have some more to do here. But there is, you could say, there was a desire by him, and there is a program that he laid forth to actually try to predict all of these things from first principles using the equations.
So we're having an ersatz lecture by you on Monday.
Yeah.
Yeah.
So we have time for something else. I mean, 3.5 and 4, it needs more time. Okay.
Other questions, comments? If not, let's thank the speaker again.